one. Good morning, good afternoon, good evening. Welcome to this special report on YouTube. I'm Kev Baker from The Kev Baker Show, and I'm joined by my good friend and my colleague, my fellow doctor in the woo, Mr. Anthony Patch. Now, we're coming to you tonight. We're adding something extra to our arsenal. There's so much information to get out there. And of course, myself and Tony, we first met when we were talking and researching CERN. Now, we're going to be getting to some big breaking news from CERN in just a moment, but let me bring Tony in right now. Tony, how you doing, man? And this is something completely new for us, something the audience we hope will enjoy, and something we're going to be doing a lot more of.
Yeah, we realized that our schedules with Truth Frequency Radio, can be kind of restrictive, even though you've been gracious enough to invite me on your show on Monday and Wednesdays, and your shows run Monday through Thursday, and then you do Freaky Friday for 3 hours on Friday, which is just crazy because that follows 2 hours with me where we're co-hosting for 2 hours, and then you roll into Freaky Friday for 3. That's a 5-hour night for you, which is crazy. But even with all those hours available to yourself and myself, there's so much information that's breaking, that's imperative that we get out. And also, not just for the sake of reporting the news, but to give it some context and to eliminate the hype and certainly eliminate the fear. So that's our mission statement for what will now be very frequent postings on your channel and on my YouTube channel as well. And I think this will help us address this issue of just not having enough time to talk about all the things that are breaking in the world of science. And, I think we'll probably branch out a little beyond science into, the world of politics and popular culture, once in a while. But again, just in the world of particle physics, quantum computers, which includes the huge topic of artificial intelligence that we've been covering, and of course, DNA manipulation. So we've got a lot to pack in. We're going to do about 20 minutes today, so take it away, my friend.
Yeah, definitely. And of course, the added extra that we get when we do it this way is the fact we have visuals as well. We can show you the articles we're talking about. We can show you diagrams, and hopefully that will help get the information across to you. And with so much to talk about before we get to the CERN news in just a moment, we're even doing something else called Entangled. Now, Tony, talk to the audience about Entangled, because edition number 2 hit the shelves today, didn't it?
Yeah, we're real happy to announce that we have a 69-page magazine that we published. We did about 25 pages last month, the premier issue of Entangled magazine. The name is taken from quantum entanglement, and this is something that Kev and I talked about, and also with my good friend from End Times Matrix News, Chris. And it's a 3-way collaboration, but what's really neat is we're offering a platform to people who ordinarily wouldn't have their own platform to get their own messages out. So it's not just myself and Kev Baker and Chris submitting articles and information. We have, this time, I think we have 12 different authors, contributors.
I'm looking at the contents here, and just for openers, you've got David Heavener on there. Now, this is a Hollywood producer, director who is making a project called The Last Evangelist. We interviewed him on the Anthony Patch Show, and that's a kind of taste of the caliber of author you find in there. We've got Ilana Freeland, Robbie and Cheryl Spencer adding music to the mix. It's absolutely amazing, Tony.
Yeah, just the table of contents is amazing. Just to look at the variety of topics and the depth that these topics go into. We talk about particle physics, of course, but we also have things in terms of MK Ultra. We have scriptures from the Bible. We have artwork from a renowned artist from Spain. I mean, we cover a lot of countries, and so it isn't just physics. It isn't just the dry, boring science. We've got a variety of things in there. Lindley Oz, one of the biggest YouTube channels out there, she is another article just like she did last month for us. So we pull from a lot of areas, a lot of directions and topics. We're also sending out from our guest on our show yesterday that I'd like you to bring up, Kev. But Dane Wigington, he has graciously offered us a 20-page PDF that he has produced on geoengineering. And that is a separate email going out to subscribers only to Entangled Magazine.
That's us, and it's just gone off. Now, like Tony was saying there, we had Dane Wigington on the Anthony Pat show last night. What a conversation this was, and I entitled it Geoengineering, a Clear and Present Danger to Humanity. Now, I urge you all to check out the information in that, because like we were talking about during the interview last night, geoengineering is something that we all face. We all breathe the same air, and it is a clear and present danger, and it's a lot more prescient and urgent than I had even imagined. So I urge you to check that out. Now then, Tony, why we're here tonight. You sent me an article today informing me that CERN are breaking records when it comes to luminosity. Talk to the audience about what's happening and what this means, because there's going to be a lot of disinformation about this out there.
Yeah, bottom line, no fear. Nothing's blowing up at CERN. Nothing is dumping. The machine is running perfectly well. And in fact, they've hit their maximum capability, their maximum luminosity, and I'll define that in a moment, of 2,556 bunches, and we'll define what bunches are. We'll break everything down. But the bottom line is they've hit the maximum number of particles that they can inject into the beams that circulate. There are two beams that circulate in opposite directions around and through the main ring, which is 27 kilometers or 17 miles in circumference. And so they refer to that main ring as the pipe. And what they've done, to use a phraseology, is they have crammed as many particles into the pipe that they can possibly fit and accelerate and then eventually collide and break these particles up. So that's just a quick snapshot. But the big headline is they are now at maximum luminosity. Luminosity simply means what happens when particles collide. It is a combination of the number of particles, the concentration, and then the number of particles theoretically that can be realized from these collisions. And therefore, the luminosity then is expressed in energy, tera electron volts, or at sometimes peta electron volts. So that's a snapshot for you, buddy.
No, that is brilliant. And, you know, when we were going over this, when it first came up, when we were first talking about luminosity, we were talking, I believe, now correct me if I'm wrong, but was it not collimators? And these are the things that tighten the bunches together. And we used to describe this as when they were using lead, particles of lead, it was almost as if all these particles were so tightly packed, it almost made like a big giant stream, like a lightsaber, wasn't it? So when I'm hearing about this, Tony, when I'm hearing about a record in luminosity, I'm thinking to myself, or to me, it's meaning we're getting tighter and tighter bunches, and the focusing, the actual collisions that are now taking place are far more frequent. Is that correct?
Absolutely correct. And, you know, I'm here in the States. I call them collimators.
Tomatoes, tomatoes, it's all the same.
Well, you know, these Scots. In fact, yesterday we had a guest on, and I couldn't even pronounce her last name, and poor Kev had to bail me out. But it was a Scottish name, so we'll go figure.
Exactly.
Anyway, I digress. Collimators. These are magnets that actually compress. Think of a pencil beam, just as an analogy, that a pencil lead that's inside a wooden pencil. And that lead, if you were to put magnets around it that could compress it from a 360-degree circle around that lead, it would squeeze that lead down and make it denser. That's what the collimators do. That's actually attached to one end of the CMS detector. But previously, last year, 2016, they compressed the beam down to 3.5 micrometers. Now what they've achieved is 2.5 micrometers, so even smaller diameter beam. And now we're going to talk about bunches. And it sounds kind of funny, but this is the actual word that they use. And we're going to have another kind of strange word in a little bit. But bunches, literally, these are packets of subatomic particles. We're going to just say protons for the sake of this discussion. And they will have literally millions of protons in one bunch. So let's just picture the bunches to be like a hot dog, and the hot dog's made up of protons. And then like a string of hot dogs that are all linked together, that's why they call them hot links, those bunches are spaced out between each other. They're not connected by anything, but they're spaced. And what they do is they actually bring those bunches closer to go together. So the end to end of the hot dogs are brought together so that they're almost touching. And that's another thing that will result in a greater number of collisions. So you bring the bunches closer together, you squeeze the bunches down and increase their density, so the number of bunches, which is squeezing the beam down to 2.5 micrometers. And therefore, when you cross the streams in some experiments, or you actually allow them to collide head-on at 99.99% the speed of light within a detector, which there are 4 of them, when they collide, they shatter. Now, you want to have as many protons, as many bunches, as tightly packed and closely spaced as you possibly can at that point of impact. And that then gives you the largest number of particles that will stream out in all directions from this point of impact within a detector. And a detector is nothing more than sophisticated cameras arranged around this area of collision. And it's taking pictures of these collisions, and it's measuring energy and spin of quantum particles and a number of other things. But that's when they talk about luminosity. It's a combination of things. It's the number of particles that can be packed together, as we described, and then it is the number of particles that are produced by the collision, and that's the other factor to luminosity. So there you go.
So I imagine these scientists, Tony, when they seen a spike in luminosity, this would have been like manna from heaven for them, because this is exactly what they're trying to achieve, right? Because then they're getting more pictures of the debris, the particles that are coming off of this when they're impacting. Or have I got that totally wrong?
No, it's exactly right. And this is why I like talking with you, because, you know, you've studied this pretty much as I have, and we have a really good understanding going between the two of us as to the science that's involved. And the reason for wanting more particles to collide and then yield more particles is because they're trying to find the primordial particles that existed at the time of the Big Bang. Now, I don't adhere to the theory of the Big Bang, but I'm using that because it's what they use to describe. What they're trying to do is find the particles that were the original particles that gave rise to our atoms and our molecules. So the building blocks of the universe, the building block of creation, is what they're seeking.
It's looking backwards in time. It's really what they're trying to do. And the best way to visualize it, for me anyway, is that I just picture cars colliding, and they're trying to get down to the very nuts and bolts of what makes up that car, that final car. And it's just the same kind of thing, only we're talking about particles here. And they're looking basically at a time that they call the moments after the Big Bang, creation, a better way to look at it. But they're trying to seek that so that they can then rebuild it artificially, Tony, from that creation point upwards.
Yeah, if you understand the mathematics of the particles and I'm using that to sort of encapsulate everything that's going on. But there's mathematics derived from these collisions within these detectors. And those mathematics can be applied to geometric shapes. So what we're looking at is the ability mathematically to rearrange the primordial particles at the time of the birth of the universe. And you're correct, they are. They're looking back in time every time they discover new particles, like strangelets that we always talk about.
Ah, the strangelets. Now, we've got a number of images as well that we want to show people, don't we?
Yeah.
I'll bring them up right now. See, this
now,
is so...
just for the audience, what we're showing you here, I'm sorry, Kev, what we're showing you here is taken directly off the public pages at CERN on their own website. This is coming from their servers. And I want to share a lot of these graphs here today, not to overwhelm you with anything technical, but just to show you this is what Kev and I look at. This is the source. This is where we go. And as we progress through some of these, I will highlight certain ones that have been used by other people on YouTube to generate disinformation and to promote fear and sensationalism. And that's the opposite of what Kev and I are all about. So go ahead, buddy.
No, it's just so much better now as well that we can add this visual aspect to what we're talking about, because it helps that the people can see. And these graphs in particular, Tony, I mean, I look at the CERN videos out there, and you're far more adept than I am at reading these things. However, it's so easy to misinterpret them, whether it's misinformation, disinformation, who only knows. But it can be easy to scare people with stuff like this if they don't know what they're looking at.
Yeah, if you see squiggly lines and something jumping up to the top of a bar graph and, a line graph, and you think, oh my gosh, it's out of control, and, the power has spiked and it's gone beyond and all this other nonsense, or they've dumped the beam. Oh, that's terrible. Oh, the machine must be about to explode because they dumped the beam. Oh, give me a break. So what we're looking at here is a graph that represents when these particles are injected. Now, particles are injected in the main ring, and then they're continued to accelerate in that ring. But stepping back from the ring, we have a daisy chain of accelerators. We actually start with a small linear accelerator and accelerate protons, other things too, but we're talking protons today. Then it enters into a ring-based synchrotron accelerator, a small version of the main ring. Then it goes to another, which is the super proton synchrotron, and it reaches about 400 giga-electron volts when it accelerates those protons. And then there is literally an injector mechanism, just like a fuel injector in your engine. And they inject these pre-accelerated particles into the main ring, whereupon the main ring, using its magnets and what they call radio frequency accelerators, if you will, pushers, they use radio frequency impulses to continue to accelerate these particles up to near the speed of light. So what we're looking at here is one of the injectors, and it's just showing, by way of this graph, the white line, it's showing the injection and then the trailing off of those particles as the last little bit of that stream of protons that were injected kind of trail off. But the peak of that is where it goes right into the main ring at the Large Hadron Collider. And the yellow squiggly lines kind of looks like an EKG rhythm or a seismograph. It just simply shows you the stability of those particles as they're being injected. Okay?
See, simple as that. Now then, which one will we go to next? We've got this one here, Tony.
Yeah, this is our friend, the Awake Linear Accelerator. Now, this is just come online November of last year. They started it and did some calibration, shut it down for Christmas, started it back up this year, which promoted a whole bunch of fear stuff that was going on YouTube. People saying, oh, Awake and all this, it's going to send particles to Italy to the Gran Sasso detector. And, the guy was saying it was Sasso Gran or something, but it's Gran Sasso. Okay, it's a former neutrino detector site. Nothing's happening. He was saying, oh, a wake's going to cause earthquakes in Italy. Nonsense. Not even connected to Italy. So here's a wake. It has a architecture that's 30 meters long compared to the 27-mile or 17-kilometer main ring next to it. They share, the same 300-foot beneath the surface chamber, if you will. It's a little off from the main ring, little chamber there. But its functioning area is only 10 meters long. So this is very small, but it has the potential of producing 1,000-fold greater acceleration in 10 meters of particles than the main ring right next door. But these have been conjoined. And that is what is going to be resulting in the opening of this doorway to other dimensions, the combining of a linear and ring-based accelerator. So I just want to show people the awake plasma cell as of today, the 1st of July. And they're not doing anything. They're doing calibrations, but they're not accelerating particles. They're not shooting anything at targets. They're not even sending particles to the north area in the center of the main ring or any of those scenarios.
And Tony, this is cool physics, because this is the one I love. It's basically the one where they put the protons or the particles they're using, and they're literally surfing on a wave of plasma. And that gives rise to this amazing jump in energies over short distances. And for me, a geek, I love the way that they're doing this.
Yeah, it's very efficient. This is a little bit bigger than the linear accelerator on a chip that we've talked about that Stanford has been producing now, literally chip-sized accelerators that likewise have 1,000-fold potential acceleration over a given distance than a ring base. So what we're looking at here is the future of accelerators. There is a lot of talk about China building 100 tera electron volt capable accelerator, other accelerators around the world. That really is old technology, but it represents an arms race, and that's kind of a divergent topic for today. You will still see ring-based synchrotrons being used. Even CERN is talking about building one now that's going to be 3 times the size and power of this ring. But at the same time, they acknowledge Tesla's work. This is Tesla's work here that we're seeing with this plasma wake field accelerator. And it's much smaller, much more efficient. And they're really testing with a wake whether it could replace the ring-based. But for now, it's going to be small scale. And if they do want to open a doorway to other dimensions, they can do it with just combining the ring and the linear, and they'll achieve that.
Amazing stuff. Now, this next one I'm going to bring up, this one gives rise to so much of the disinformation.
Did I lose you?
Are you there, Tony? I'm here.
I've lost you, Kev.
Okay. Now, this graph here, this is the one, Tony, that I've seen leading to so much confusion, so much misinformation, disinformation. Talk us through this.
Yeah, again, we're looking at different perspectives on the beams themselves. We have both beams. If you look at the top of the chart, in blue is beam 1 and red is beam 2. And then as we slide over to the right, you see 6.50 tera electron volts, TeV. Now, 6.5 TeV is just for one beam. When they collide, we add those two together, and that's where we get our 13.5, sometimes 14 tera electron volts. And so if we go along with the graph, we see in the upper left corner, it says beam intensity and energy. And all they're representing there is the integrity of the beam itself. It's showing you as the graph will swing up, it will show you how many tera electron volts are being achieved, and that's on the right-hand side, as Kev is showing, all the way up to 7 being the maximum per beam. When a beam dump occurs, this line will drop dramatically down to the bottom. So what we're seeing here are actually two beams, and you will also see a target at times. So to break this down, we have a blue line, that's beam 1, and the red line is beam 2. The green line that you see there is what their target is. That's the shape of the beam or their energy profile that they're trying to achieve. Now, they weren't successful here, but it may not have been their intent. It's just giving you a reference as to the power curve for both beams that would represent the ideal of that is that green line. So moving to the right, we're looking at the individual beams themselves again. Blue is beam 1, and they're showing you the stability of that beam. And as you move from the bottom left corner of that going up, it is showing you the stability and the integrity of the beam. That blue dot, for example, if it was not stable, would be much larger. It wouldn't be squeezed down like we described with the collimators, the magnets that squeeze it down. What you're seeing here is a good tight beam. It's been squeezed by the collimators, and that would be appropriate for a collision to take place with that shape of beam. You're looking at the cross-section of the beams or the bunches we described. If you look at the next one, says beam lifetime. That, again, just as the name implies, is the length of time that the beam is held together is stable, and the time in which it's circulating around the main ring itself. And if that were to break up or the peaks were to drop down, that would mean that the beam has become unstable, that they're not having a tight packing together of the bunches. We like to talk about it in terms of the pencil lead. It is not lead, but as a pencil lead analogy, it would be like breaking up that pencil lead into sections that would then result in a graph that doesn't have good power curve to it. Now, this isn't a good power curve here. This is not a good bunching together. It's not a good solid beam. But this is all representing what they call machine development. If you go to the upper left-hand corner of the entire page there, it says LHC, and it gives you the run number, and then it says machine development. That's just calibration. They're sending test beams in. They're testing their instrumentation. They're also testing the magnets and the detectors. And they're also testing to see if there's any contamination within the pipe, because oftentimes you'll get leftover electrons on the walls of these pipes. And that causes a breakup in the beams and reduces the luminosity, the ability to collide efficiently. So that's what's going on. Let's talk about luminosity. Come down on the left-hand side there, Kev, and we see luminosity. And again, this is both beams. It's not a full complete graph because they're not running two sets of full beams. But what you would see there, again, would be an energy profile. You would see the number of particles represented as, and the number of bunches represented as the higher elevation of that graph curve. The higher up that graph curve means the higher the luminosity. That just means you have more bunches and more particles closely packed together. Like we said, 2,558, I think it was. Let me look at my notes here.
56.
2,556, yeah. So that would be the top of that chart that we're looking at there. Now swing to the right there, directly across to the right, it says standby, standby, standby. Those are detectors. So we've got Atlas, Alice, the compact muon solenoid, CMS, and then the LHCb. And the one that we tend to focus on a lot is Alice, because that's where they are realizing strangelets. They're in standby mode because they're not actively filling the pipes to capacity, and they're not colliding anything. So all the detectors are in rest mode at this point. Tune feedback, that is related to the injectors and whether they're being efficient. There's no breakup in the injections, and it also has to do with what I mentioned a moment ago, and that is using radio frequencies to push these protons in the main ring and continue the acceleration. So that is tuning those radio frequency pushers. That's what that also represents. Orbit feedback at the bottom is just saying whether or not the orbit has a true path. The path that they're trying to achieve is the center point of this pipe. They have magnets. They have dipole and quadrupole magnets, and they are designed to keep that squeezed down beam in the center of the pipe so that it doesn't stray off and contact the inner walls. And these walls of the pipes are metal, but they need to keep them in the center so that they don't touch the walls, which would be, just an immediate shutdown. It's not going to mean the machine's going to blow up or anything. It dumps the beam into the north area immediately. It's magnetically directed. And by keeping it in the center point, they are able to achieve the highest speed possible. And if it's in the center point, your aim is better. It's just like a bullet coming out of a rifle. You want to be able to aim the beams from the center point, because that center point in the pipe is what then produces the center point, the crossing over of the beams within the detectors, resulting in these collisions. So nothing going on here. Everybody's in rest mode. They're getting ready. Later on, we're going to show you the schedule. It's called the injector schedule for the LHC. And we'll break that down. It's easy to read, but we'll show you what's coming up next.
There you go. Injector schedule just on command, Tony.
It's only because you're a master at doing this.
Something like that. But this is an invaluable resource tool, because you see so many times people hyping things up, but then when you actually look at the schedule, which comes from CERN themselves, it tells you that they're doing calibration tests, stuff like that, Tony. So what's some of the highlights to look out for the rest of the year?
Yeah, this is kind of a strange calendar to look at, because it doesn't really run like a normal calendar. It's CERN, so what else would you expect?
Exactly.
They're going to complicate. Even the calendar has to be complicated. But if you go to your favorite search engine and you type in injector schedule, CERN, let's start off with CERN. It would be CERN Injector Schedule 2017. You'll see this PDF. Easy to find. Let's talk about the months. Okay, up there they have July and August and September. And below that they have numbers, 27, 28, etc. Those are the weeks. Those are the weeks of the year. And what is confusing is you have to actually pay attention to the blue boxes where they have numbers as well. And across the top there you'll see 10 and 17 and the others. I can't quite read them, but it doesn't matter. The blue box has numbers in it. Those are the actual date of the month, like the 10th day of the month, the 19th or 17th day of the month. So focus on those. Don't look at the week numbers. That'll just confuse you.
This one here, this is the best one. We've got a 3 in the box directly beside the Monday. It's week number 27, and that's where people get confused. But just disregard the weeks. You've got July 3rd, Monday, and that is this coming Monday. And like Tony says, it jumps to the 10th, the 17th. You've seen the pattern now. It goes forward in weeks. And once you get that sussed, it's plain sailing, isn't it?
Yeah, you just go down the blue boxes from 8, and then it would be 9, 10, and so forth, and then shift over to the other column. Thank you, sir. There we go. So that's basically how you read that. The definitions here, let's go above July. It says W27. That means week 27, Large Hadron Collider, technical stop 1, TS1, technical stop. Technical stop just means that they're not injecting any particles, they're not creating any beams, and they do that periodically because they're going to make adjustments, or they're preparing for a specific experiment to take place with one of the detectors or multiple detectors. And so this one is a technical stop. If you go down that column, it says technical stop 36 hours. And that means that's how long the machine is down, and then they'll be getting ready to inject. So you go over to week 28, and it says injector, and it says 10 hours. And that's where they're beginning to inject, and it's injector machine development. MD is machine development. Again, just a broad-based statement saying that they're getting the machine set up, they're testing everything in preparation for injecting. Let's go on over. We've got sort of the grayed out on the 24th there. There's 2 boxes there. I want you to look at that, Kev, because that's new. And go ahead and scroll all the way down to the bottom of the page to the legend.
We've got more of them here as well, along on week 37. And if we go down, like Tony says, there is an actual legend here. And it says that this represents LHC, machine development, block proton period.
And all that is they're setting up for protons to be injected. And this isn't something they've had in previous years on their calendars, but I think they're just making it clearer
Tony,
as to
this one here,
what they're injecting.
This technical stop, because this is an important one as well. I mean, really, it's nothing sensational. They're just shutting down for a period of time. But this is the one that I've seen where people go apeshit crazy, right? Because they think, oh, the beams are being dumped. Catastrophe must be imminent. There's lights in the sky. We've heard it all before. But it's just they're closing the machine down. It's a machine. Sometimes it stops, right?
Yeah, people have to realize that there are multiples of experiments that are done with this machine for a variety of countries and agencies, laboratories that are all partners. They're actually member states. And so they buy machine time. They schedule machine time for a variety of different experiments. And they do this with synchrotrons all around the world. Did we lose our signal there, Kev?
No, we're back. We're here.
Yeah, your graphic is breaking up at my end here.
It's okay this end. I think we're okay.
Right. Okay, so progressing on, let's jump ahead real quickly so we don't run out of a lot of time. Let's go down to this orange area for October, November, December.
This must be catastrophe. It's orange, Tony. It must be doom and gloom, right?
Warning, warning. Yeah. So go to the top of week 43. It says end north area proton physics. That's what that means. Okay. North area. That's the center point of the main ring. That's where they dump the beams, but they also do experiments at that impact point. And that's in preparation for this conjoining of a wake. So let's slide to the right, and you're going to see next to November at the top there, beam to a wake for setting up. And down below it says North Area Xenon Physics. Xenon is a poisonous, inert, colorless, odorless, tasteless, but poisonous gas. And they're going to be using that in various chambers and impacting in that gas field accelerated particles. But we've talked about a wake being conjoined with the main ring. Well, there it is right there. Beam to a wake for setting up.
And people have said that you've been way off the mark with that. And we've proven now a couple of times, and this is from CERN's own website, beam to a wake for setting up. It couldn't be more clear, Tony.
That's it. And what they're not showing you here on this injector schedule is the fact that they will be targeting the north area with accelerated particles coming out of, if you will, out of the rifle barrel of the linear accelerator awake. So here it is right here, folks.
Now we've got
this. Big deal.
We've got a little slither here. Now it says here, high radiation material, I'm thinking. Possible beam request. Is that anything of interest we need to be watching for?
Just the fact that they are going to have a higher than normal radiation signature from the materials that they're experimenting with, and that's in the Large Hadron Collider Machine Development 4 phase. And again, that is a testing phase. What that really means is that they have radiation shielding, they have radiation producing experiments within that shielding, and it's a high hazard, notice, but they may want to use beams in those experiments. And so it's just an option that they're indicating to the injector operators that they may want to use beams at any given time in those days in which they're running high radiation experiments.
And like we've said, you can find this easily. This is no inside information, nothing like that. Just go to Google, Bing, whatever engine you use, and type in CERN injector schedule. It's there for everyone to see. Now then, let's go to the next image. What we're looking at here, this looks like a whole heap of numbers. It looks like bingo or something going on, Tony. What's going on?
It reminds me of going to the airport and looking for my flight. Jeez.
The only thing missing is the cancellation at the bottom.
Oh, yeah, those are all the cancellations. That's where the world came to an end.
So what's happening here, Tony? Because I can imagine there's a lot of confusion with this.
Well, we're going to pretend that this is Logan Airport in Boston. Okay, that's a little inside joke between me and Kev. SPS larger 1. That is the super proton synchrotron. That's the one I mentioned that pre-accelerates particles just before they go into the main ring, and that's about 40 giga-electron volts. And what they're showing you there are the targets for those beams that are being injected. And if you look over, you'll see INJ, that's injector. And all those numbers represent, really, when you look at 1589, 1539, that's the number of bunches. And those are 2 beams of bunches. And that's all that is. And when it says percentage of loss, that's 2.8% of the protons in the bunches that have actually been lost during the injection process. That's all that means. Okay?
Cool.
So then we go down to inject down in the lower group, and it's showing giga electron volts. So you have 20 giga electron volts at the speed of light, or /c, and then you have 27 giga electron volts at the speed of light. And again, it's 1/1000th of a percent below the speed of light. But those are the 2 beams. Those are their energies in giga electron volts while they're being injected, and then they'll move up to tera electron volts as they're accelerated in the main ring. So that's pretty straightforward. Nothing complicated there.
And of course, when we're talking about these volts, it's the fact that they're so tightly packed together in bunches, constantly colliding, that gives birth to these energies, isn't it, Tony?
Yeah, it's interesting you bring that up. Good segue. Go to the bottom and it says loss, and then it says FB 2.2% on the left-hand side, okay? Those are the femtobarns. Femtobarns. We're going to talk about femtobarns in just a moment.
Femtobarns. So, I will bring you up femtobarns right here. There you go, Tony.
Now, this is kind of interesting. There's a little history for the audience. They derived the name barn back when the Manhattan Project was involved, and they were working at Los Alamos, and they were developing, the first atomic bomb. They needed targets to be impacted, and they were kind of kidding around saying that you couldn't hit the broadside of a barn. Okay. And so the target they called a barn because they had to make the target so large in comparison to what they do now at CERN. When they hit a target with a beam, they had to make an oversized target because their ability to control the beams during the Manhattan Project was so rudimentary. They just had an oversized barn. So they said, well, let's just call it a barn because it's a big target. Maybe we can hit it.
That's a good enough reason, I'd imagine.
Might as well. I mean, you've got pipes and you've got bunches and, come on. So a barn is a unit of area equal to 10 to the minus 28 square meters. And then they translate that to femtometers. And femto is simply a unit of measure combined with the size of the target. So scroll on down and you're going to see a conversion table. Keep going. And there we are. Okay, right. Hang on. Slide up just a little bit. There it is. Okay, femtobarn is right there. You see picobarn, femtobarn. Femtobarn is FB. And when we look at a chart that's coming up here in just a moment, it's going to list FB. I think that was the first luminosity chart you had. The left-hand vertical column of the chart had FB as the measurement scale. Let's go to the very, very first. Keep going back to the very first of our presentation. And Uh, didn't we hit a luminosity?
I think
It was 20.
it might be on this one here.
It was the one that, there it is, the 2016. Perfect. Very good. So FB is in the upper left-hand corner. That's the femtobarn scale, and it says delivered luminosity. They're measuring the size of the target. They are describing the number of particles that are impacting that target in that delivered luminosity scale. So the higher up we go, the higher the luminosity, the larger the number of particles colliding. And now we see at 2017, we see 13 tera-electron volts. That's the combination of two beams, their combined energies totaling 13 TeV. The colored chart shows that these luminosities, the yields, are increasing steadily. And that's why they get all excited about luminosity, is because it represents more and more particles successfully colliding. And because they're successful, it's yielding a greater number of smaller primordial particles like quarks and muons and gluons, and on out to 1,000 numbered, named quantum particles that to date they have discovered.
And Tony, just looking at this graph here, I mean, if it carries on the kind of projection that it's on just now, we're talking about it going shooting right up like that.
Yeah, and if we are talking here, let me see if I have the number in femtobarns in my notes. I might have it here. When we're extrapolating that, we're actually going to the top of that chart. And I don't have it in this article, but if you do take that and extrapolate it, they are going for the maximum number of particles that they can contain within those pipes. So essentially, we're going to 45 femtobarns is what they're shooting for. So far today, to date, they have realized 13 TeV. They will not exceed that. They might go to 13.5, but they're really not shooting for a higher power at this point. They're just looking for a greater number of collisions, the higher luminosity. So we can extrapolate the line, and it'll take it right up to the top of that chart. And that's the maximum the machine can achieve. They will not be able to until they change the magnets out over the next 3 years, starting in 2018. They're going to be swapping the magnets out so that they can increase the luminosity and therefore the energy as well. So this is machine development. Did you want to say anything? I'm kind of compromising everything.
No, you're doing brilliant. I'm just bringing up the next image here. It says LHC cryogenics, page 1.
Yeah, cryogenics by the name is cold. Now the environment inside the pipe is super cold because the magnets in that environment are superconducting. Superconducting simply means you're cooling things to such a point that, and it's near zero, absolute zero, but not quite. You're reducing the temperature so that you reduce the resistance and allow the freer flowing of electrons. And just like your toaster, that has a lot of resistance in the wires on purpose because you want heat for toasting. You want the opposite to occur within the pipes of the main ring. So they cool the magnets to increase the electron flow, which also makes the machine more efficient so that they don't have to draw as much energy from the grid that is supplying CERN. So it makes it a more efficient machine. What you're looking at the very bottom is the average arc temperatures. Now, that's the arc temperature of these electrons flowing through the superconducting magnets. And if that line were to rise up along the chart, it'll stay horizontal. You usually don't see peaks in this chart. It stays relatively flat, but it'll climb up the ladder of the chart if the temperatures begin to rise. Now, right here, it's stable. But when they're actually running beams, they're not doing it now, but when they'll start running the beams, you'll actually see this line drop down slightly to about midpoint to where it is now. But this is normal. It takes actually, when they shut the machine down completely, at the end of a run. We're in run 2 now. When they shut it down at the end of run 1, it actually can take anywhere from 3 to 4 months. It depends on if they swapped out components or not in the ring. But generally speaking, it takes 3 to 4 months to cool the machine down to the temperatures that we're seeing here so that they can achieve that superconducting environment for the magnets. But also inside the pipes are filled with helium, again for cooling, and the pipes otherwise are in a vacuum. Okay?
Wow. Awesome. Always learning new stuff. I love this. Now then, I've seen this graph often as well. We've got the energy levels up here on the right-hand side. We've got beam intensities. Tony, what else do people need to know about this one here?
Yeah, I want to correct myself. I said that the helium for cooling is inside the pipe. The pipe's an absolute vacuum. You can't have anything in there. But it cools the helium is actually used to cool the magnets down to that supercritical superconducting state. So I want to be very specific. Okay, so we're looking at this. Again, we have Atlas, ALICE, CMS, and LHCb, the 4 principal detectors where the beams are crossed or collided head-on. Nothing's going on, as we said earlier. Everything's in standby mode. If we look at the LHCb velo position, we're looking at gap and we're looking at totem and standby and adjust. Then we look at this luminosity curve. Again, all we're looking at is not luminosity curve, excuse me, the intensity curve. These are the beams. And when you look at the red line and the blue line, those are the 2 separate beams there. When you look at the black line, what that is showing you is their idealized curve that they're trying to achieve. Everything's in standby, so it really doesn't apply to what we're seeing here. But that black line, when they are running, will have an idealized curve that they're trying to match the 2 beams to. Okay?
Awesome. And we move on. Now this one, this looks gobbledygook to me, Tony. This is the collimators. Now, these are the things we were talking about that push these protons tighter together, isn't it?
Yeah, the collimators. And are you going to shift to that one? Because I'm still seeing the detector status.
Okay, 2 seconds.
Well, we're back at Logan International in Boston Airport, and we're checking our flight and gate statuses here on the board.
It really does. It looks like I've lost my luggage again by the looks of it.
Yeah, your luggage is over in those little red areas. It looks like yours went to TCDD.4L2.
So what does this all mean? I mean, are these segments of the collimators themselves, Tony? Is this what this is?
Yeah, exactly. These are individual magnets that are squeezing down the beam, and they're showing their relative energy, their magnetic strength, and whether they're stable, whether there's one that has to be swapped out or not. And again, because they're in standby, it really doesn't mean much. You're going to have a broad variety of numbers there, but once they go to squeezing down the beams, all the numbers will stabilize and they'll look very much the same. That's the ideal, is they all want to have the same configuration numbers.
Okay, so we'll go to the next one here. It's just the same again, and of course...
Yeah, this is now beam 2. The first one we looked at was beam 1.
Now we've got
this is beam 2 with its attendant collimators, as you say. I want to say colanders now.
Colanders. Now here's one that I have seen used quite a lot on YouTube. What are we looking at here?
Yeah, again, we're looking at the detectors listed on the left-hand side. The right-hand side is showing the 2 beams in Atlas or any of the other 4 detectors, and the target in red. And bring that up a little bit for me if you can magnify that for me. There we go. Okay, now that's showing the luminosity. It shows the delivered beam within Atlas in this particular example, and the target means the target is the number that represents the luminosity that they want to achieve, Now, in this case, they were able to deliver a higher luminosity than their minimum target range for that given experiment. So that's why it's in green, because it was a positive result and they exceeded what they were after. And that speaks to the greater topic here today, that the machine has actually been exceeding by about 10%. It's been exceeding their expectations as to the luminosity that they were seeking. So they are well ahead of their initial projections for luminosity this year.
And of course,
so they've been very successful.
Every winter there's a shutdown, and it's always a fine tuning. It's either new magnets, new collimators, always trying to improve on the model from the year before. And like you say, this year it seems to have been really successful, Tony.
Yeah, I'm going back and looking at my notes. Yeah, the peak luminosity reached in 2016 was 1.58 times 10 to the 34th cubic meters to the minus 2 power, and they were, again, it says a good 10% more than the 2016 record of 1.4 times 10 to the 34th. So they went from 1.4 to 1.58 10 to the 34th number of particles, let's say protons. They use electrons, they use photons, they use ions of lead. Depends on their experiment within the beam itself.
Now, this one here, this is basically the one we were looking at on the website, isn't it?
Yeah, again, we're back to the femtobarns. And femto is just a unit of measure. I mean, it's extremely small. It's like almost like a Planck scale size of measurement. So very, very small. But you see the projection, the dotted line is the projection. And this graph here is only including last year's data of 2016. But the dotted line is their extrapolation. And I think now what they have realized. But that's a projection on out into the latter part of this year. So as I said earlier with the other chart, they're almost to the top of their maximum capability with this configuration of magnets that they have. They're using, by the way, the magnets are made of the superconducting, super cold magnets are niobium and titanium. They're going to switch out over a period of almost 3 years after beginning in 2018 to niobium and tin. So swapping titanium, bringing in tin. That's going to give them the ability to hit, rather than 13 tera electron volts, the ability to go to anywhere from 20 to perhaps as high as 50 tera electron volts. But I also want to emphasize we're into new physics by their own admission, by bringing in the linear accelerator awake. And because of the new physics, that's the term that they assign to this conjoining of these two accelerators. If it is their intention to open this doorway to other dimensions this year, they will need to go beyond tera electron volts and into peta electron volts. And by my calculations, looking at the machines themselves, the magnets themselves, the capabilities of the magnets themselves, it appears to me that what they need in order to separate the quark-gluon condensate, separate the quarks from the gluons, which represents the strong force, the nuclear force. In order to separate the quarks, they need 20 peta electron volts. Now we're up into the quadrillions of energy. So go ahead, Kev.
No, well, I mean, when you look at the way the machine's going, it's certainly not out of the realms of possibility, is it? Because it seems to be just always improving, always getting closer to that kind of golden number that they're trying to attain.
Yeah, and I got to tip my hat to them. I mean, you look at this from an engineering standpoint, just the machine itself. This is remarkable. They really have achieved some great milestones in an engineering aspect. But we spent a lot of time talking about the occulted agenda and the spiritual side of that, and we're going to kind of sidestep that today because our goal in this presentation was to stick to the facts, stick to the data, be able to share with you what we look at to understand their activities and understand their goals, and to clarify and try to remove some of the fear and some of the misinformation and the hype, as we've been repeating over and over again. And so we wanted to have kind of a calm, deliberate, continuous train of thought discussion here today without commercial interruptions. And for you as the audience to just kind of have a fireside chat that you get to, listen in on and observe with Kev and myself here. And we're going to do many more of these. So, if you want to hear the real science, if you want to hear what's going on at the tip of the spear, whether we're talking CERN or you're talking quantum computers or DNA, Kev and I focus on the tip of the spear, the leading edge of what's going on, what's breaking in the world of science. You can sit back, rest assured that Kev and I have our finger on the pulse of what is going on in science as much as we can, but the information is just coming at us like a fire hose. And we've said that before. Last year, I made that statement, and it's only worse now. Now we've gone from an 1.5-inch fire hose to a 5-inch fire hose in terms of the quantity of information that's coming to us. And we really have broken the news on a lot of fronts, well ahead of YouTube land, as I like to call it, even though this video is on YouTube land. I really encourage you as the audience to trust us that we are giving you the straight information without creating unnecessary hype. We'll kid around about it. We'll kind of poke fun at these guys, but we take this very seriously in terms of our research. And we have said many times, we look at their information. We look at the journals. We look at the scientific publications. And even the magazine Science itself, in which articles from laboratories are published, or excerpts of them, they even dumb it down. They don't even go to the extent of explaining and defining words and telling you really what's going on. Even in Science, that's the name of the magazine, and there's Nature and there's others. And what Kev and I do is really go beyond even those magazines to define unfamiliar terms, to put it in a context that intuitively you can relate to, so that you can use that information so that you gain a better understanding. And to that end is also the purpose of my magazine that Kev has up here called Entangled. And so I spend a great deal of time putting together, I think this time I have 8 articles in there, maybe not that many, but 6 or 8 articles in there. And I talk about quantum computing and I talk about particle physics and get into the nuts and bolts of it. And that's another extension of these videos that Kev and I are doing. Sometimes it's nice. Some people like to learn by listening and seeing the graphics. Some people like to sit down with a piece of paper or a magazine and learn it that way. So we try to cover all different learning methodologies. And, it's really a personal message from myself and Kev that you support us. I'm being really quite candid with you here, that you support our efforts. We don't have grants from think tanks and from universities and from DARPA. We get supported by listener participation, supporting us at Truth Frequency Radio by subscribing to us, subscribing to the Entangled magazine. That helps us. That supports us. Watching our YouTube videos. Yes, these will be monetized videos, not crazy monetization, but these are going to be monetized videos, so that goes to support what we're doing for you. Kev, what do you have for thoughts on that?
No, I'm really loving this. Like I say, it's an extra weapon to our arsenal because there's so much information coming right now. I mean, we're deep into it when it comes to AI. Today, CERN, it seems like a while since we've spoken about CERN, Tony. And that's why I thought I was quite keen to get this information out there, get it out there fast. But we do need your support as well. And if it's via TFR by signing up for either of our shows, we actually share in the subscription. That's one way you can help. You can also get Entangled e-magazine. It's not an extortionate price by any means at all. Just go to anthonypatch.com. And that way, that enables us to keep going, keep researching. Right now, I'm not working, so I've got 24/7 to dedicate to all of this information. And I'm going to do that because it's important that everyone, especially at this time, gets their head around the kind of topics that we are covering. And like I say, it'd be so easy for me just to disregard Anthony and go and clickbait people, sensationalize all of this CERN, this AI stuff. It'd be really easy to do, but I'm not about that. We're about the truth. Might not be quite as exciting. It might not have all the bells and whistles that you see on some of the channels, but we're real people and we're bringing you real truth. And of course, Tony will be back on Monday night, right, on KBS. Any plans for that?
Yeah, we're going to continue talking about color and the spiritual aspects of color and light and how that relates to quantum computers and also artificial intelligence, something that we've really been digging into on our shows and also in both of my issues of Entangled magazine last month and this month, deep into explaining the latest in artificial intelligence. In fact, D-Wave, just as a side note, real quickly, D-Wave internally is undergoing a paradigm shift insofar as how they are operating their machines from a software standpoint. They will be publishing later on this year, I expect probably within 30 days, a seminal paper from them, from D-Wave, discussing the Boltzmann machine. And this is a form of stochastic mathematical sampling is a good way to just quickly summarize that. The Boltzmann machine is related to recurrent neural network learning or programming. This is the machines teaching themselves, writing their own code. Recurrent neural network programming is all part of the Boltzmann machine of data sampling and classification. This is a huge departure from feed forward, which is basically a 9-step linear process of processing information resulting at the 10th step with a solution, oftentimes used with speech recognition, handwriting recognition, and facial recognition. That's Model T stuff. So we're already talking about it on our shows, Kev and myself. We're already talking about it in the Entangled magazine. We're way ahead of D-Wave, even publishing their own paper about their own paradigm shift to the Boltzmann machine. And the Boltzmann machine, as Kev is showing you here, geographically, if you will, is my model of the universe, the 600-cell tetrahedron. They are one and the same. And I'm going to leave you with this parting thought. I'm anticipating a number of people in the Christian community, because I am a Christian, pointing fingers at me and saying heretic, blasphemy, New Age, because you use as your model of the universe what they would call sacred geometry. Well, sacred geometry in New Age is a mirror. It is a copy of God's creation. So for me to use God's geometry and mathematics, because he created that, is part of being a Christian. I'm simply sharing you.
I'm sitting smiling here, Tony. Imagine criticizing you for actually using sacred geometry. I mean, what makes it sacred? To me, it's sacred because it's God's geometry.
I agree, and that's what Satan does. He will twist things around to his own purposes, and that's what they've done in the New Age parlance, and that's what they've done with the Enochian mathematics and language. They twist it all around, but it's perfectly in keeping with my faith to be talking about the Boltzmann machine, tetrahedrons, 600-cell tetrahedron. What is really known in mathematics, the 600 cell is actually known as the E8 Langrarian mathematical representation. So that's a mouthful. An E8 Langrarian is what that image there that Kev is showing you, that I call, because it's easier to talk about it, as a 600 cell tetrahedron as my model of the universe.
Well, Tony,
all right, my friend, wrap it up for us.
We are almost out of time. I'm saying we're almost out of time. We have no time constraint. But this was meant to be 20 minutes. And, you know, just like our email exchanges, this is the way it goes. We just kind of sync up. We love talking about all this stuff. We're passionate about it. And the fact we can deliver it to you in this form now as well, just a bonus. Now remember, we'll be back on Monday, 11 p.m. in the UK, 6 p.m. on the East Coast, 3 p.m. on the West Coast, on the number one talk network, truthfrequencyradio.com. You can join us in the chat room, truthfrequencyradio.com/chat. Myself, Anthony Patch, and the one and only Johnny Whistles will be there, getting into colours, light, and all the good stuff. From me and Anthony Patch, have a very nice weekend.
Variety of things in there. Lindley Oz, one of the biggest YouTube channels out there. She is another article just like she did last month for us. So we pull from a lot of areas, a lot of directions and topics. We're also sending out from our guest on our show yesterday that I'd like you to bring up, Kev, but Dane Wigington, he has graciously offered us a 20-page PDF that he has produced on geoengineering. And that is a separate email going out to subscribers only to Entangled Magazine.
That's us, and it's just going off. Now, like Tony was saying there, we had Dane Wigington on the Anthony Patch show last night. What a conversation this was, and I entitled it Geoengineering, a Clear and Present Danger to Humanity. Now, I urge you all to check out the information in that, because like we were talking about during the interview last night, geoengineering is something that we all face. We all breathe the same air, and it is a clear and present danger, and it's a lot more prescient and urgent than I had even imagined. So I urge you to check that out. Now then, Tony, why we're here tonight. You sent me an article today informing me that CERN are breaking records when it comes to luminosity. Talk to the audience about what's happening and what this means, because there's going to be a lot of disinformation about this out there.
Yeah, bottom line, no fear. Nothing's blowing up at CERN. Nothing is dumping. The machine is running perfectly well. And in fact, they've hit their maximum capability, their maximum luminosity, and I'll define that in a moment, of 2,556 bunches. And we'll define what bunches are. We'll break everything down. But the bottom line is they've hit the maximum number of particles that they can inject into the beams that circulate. There are two beams that emitters. These are magnets that actually compress. Think of a pencil beam, just as an analogy, that a pencil lead that's inside a wooden pencil. And that lead, if you were to put magnets around it that could compress it from a 360-degree circle around that lead, it would squeeze that lead down and make it denser. That's what the collimators do. That's actually attached to one end of the CMS detector. But previously, last year, 2016, they compressed the beam down to 3.5 micrometers. Now what they've achieved is 2.5 micrometers. So even smaller diameter beam. And now we're going to talk about bunches. And it sounds kind of funny, but this is the actual word that they use. And we're going to have another kind of strange word in a little bit. But bunches, literally, these are packets of subatomic particles. We're going to just say protons for the sake of this discussion. And they will have literally millions of protons in one bunch. So let's just picture the bunches to be like a hot dog, and the hot dog's made up of protons. And then like a string of hot dogs that are all linked together, that's why they call them hot links, those bunches are spaced out between each other. They're not connected by anything, but they're spaced. And what they do is they actually bring those bunches closer together. So the end to end of the hot dogs are brought together so that they're almost touching. And that's another thing that will result in a greater number of collisions. So you bring the bunches closer together, you squeeze the bunches down and increase their density, so the number of bunches, which is squeezing the beam down to 2.5 micrometers. And therefore, when you cross the streams in some experiments, or you actually allow them to collide head on at 99.99% the speed of light within a detector, circulate in opposite directions around and through the main ring, which is 27 kilometers or 17 miles in circumference. And so they refer to that main ring as the pipe. And what they've done, to use a phraseology, is they have crammed as many particles into the pipe that they can possibly fit and accelerate and then eventually collide and break these particles up. So that's just a quick snapshot, but the big headline is they are now at maximum luminosity. Luminosity simply means what happens when particles collide. It is a combination of the number of particles, the concentration, and then the number of particles theoretically that can be realized from these collisions. And therefore, the luminosity then is expressed in energy, tera-electron volts, or at sometimes peta-electron volts. So that's a snapshot for you, buddy.
No, that's brilliant. And, you know, when we were going over this, when it first came up, when we were first talking about luminosity, we were talking, I believe, now correct me if I'm wrong, but was it not collimators? And these are the things that tighten the bunches together. And we used to describe this as when they were using lead, particles of lead, it was almost as if all these particles were so tightly packed, it almost made like a big giant stream, like a lightsaber, wasn't it? So when I'm hearing about this, Tony, when I'm hearing about a record in luminosity, I'm thinking to myself, or to me, it's meaning we're getting tighter and tighter bunches, and the focusing, the actual collisions that are now taking place are far more frequent. Is that correct?
Absolutely correct. And, you know, I'm here in the States. I call them collimators.
Tomatoes, it's all the same.
Well, you know, these Scots. In fact, yesterday we had a guest on, and I couldn't even pronounce her last name, and poor Kev had to bail me out. But it was a Scottish name, so we'll go figure.
Exactly.
Anyway, I digress.
One. Good morning, good afternoon, good evening. Welcome to this special report on YouTube. I'm Kev Baker from The Kev Baker Show, and I'm joined by my good friend and my colleague, my fellow doctor in the woo, Mr. Anthony Patch. Now, we're coming to you tonight. We're adding something extra to our arsenal. There's so much information to get out there. And of course, myself and Tony, we first met when we were talking and researching CERN. Now, we're going to be getting to some big breaking news from CERN in just a moment, but let me bring Tony in right now. Tony, how you doing, man? And this is something completely new for us, something the audience we hope will enjoy, and something we're going to be doing a lot more of.
Yeah, we realized that our schedules with Truth Frequency Radio, you know, can be kind of restrictive, even though you've been gracious enough to invite me on your show on Monday and Wednesdays, and your shows run Monday through Thursday, and then you do Freaky Friday for 3 hours on Friday, which is just crazy because that follows 2 hours with me where we're co-hosting for 2 hours, and then you roll into Freaky Friday for 3. That's a 5-hour night for you, which is crazy. But even with all those hours available to yourself and myself, there's so much information that's breaking, that's imperative that we get out. And also, not just for the sake of reporting the news, but to give it some context and to eliminate the hype and certainly eliminate the fear. So that's our mission statement for what will now be very frequent postings on your channel and on my YouTube channel as well. And I think this will help us address this issue of just not having enough time to talk about all the things that are breaking in the world of science. And, you know, I think we'll probably branch out a little beyond science into, you know, the world of politics and popular culture, you know, once in a while. But again, just in the world of particle physics, quantum computers, which includes the huge topic of artificial intelligence that we've been covering, and of course, DNA manipulation. So we've got a lot to pack in. We're going to do about 20 minutes today, so take it away, my friend.
Yeah, definitely. And of course, the added extra that we get when we do it this way is the fact we have visuals as well. We can show you the articles we're talking about. We can show you diagrams, and hopefully that will help get the information across to you. And with so much to talk about, before we get to the CERN news in just a moment, we're even doing something else called Entangled. Now, Tony, talk to the audience about Entangled, because edition number 2 hit the shelves today, didn't it?
Yeah, we're real happy to announce that we have a 69-page magazine that we published. We did about 25 pages last month, the premier issue of Entangled magazine. The name is taken from quantum entanglement, and this is something that Kev and I talked about, and also with my good friend from End Times Matrix News, Chris. And it's a three-way collaboration, but what's really neat is we're offering a platform to people who ordinarily wouldn't have their own platform to get their own messages out. So it's not just myself and Kev Baker and Chris submitting articles and information. We have, this time, I think we have 12 different authors, contributors.
I'm looking at the contents here, and just for openers, you've got David Heavener on there. Now, this is a Hollywood producer, director who is making a project called The Last Evangelist. We interviewed him on the Anthony Patch Show, and that's a kind of taste of the caliber of author you find in there. We've got Ilana Freeland, Robbie and Cheryl Spencer adding music to the mix. It's absolutely amazing, Tony.
Yeah, just the table of contents is amazing. Just to look at the variety of topics and the depth that these topics go into. We talk about particle physics, of course, but we also have things in terms of MK Ultra. We have scriptures from the Bible. We have artwork from a renowned artist from Spain. I mean, we cover a lot of countries, and so it isn't just physics. It isn't just the dry, boring science. We've got